it's something that's particularly close to my heart is tactile stimulation and oxytocin. And obviously, the vowels are pretty tactile, during the comforting. And I just wanted to whether to some extent you managed to distinguish, whether or how important that tactile component is for bonding, for the comforting, and so forth involved.
Yeah, we haven't done much with that. I mean, definitely, real social interactions is much more effective and salient to the vocals than being, say, behind the cup. So, in many mouse studies, they do the social recognition and different exposures with other mouse behind the cup, so they can smell it, they can see it. They can't get the whiskers on it. And we find that makes a big difference. But that's also true in mice. So I know that people who have studied social recognition in mice, and if you have the cup with the holes are too small, so they can still see really, but they can't really get in there and touch. They can't perform the social recognition as well. So I think you're exactly right. And Shlomo Wagner has a paper, or maybe it was, I can't remember if it was a real paper or a preprint, where they showed that actually auditory, visual, and somatosensory cues are all important for social recognition in mice. I can't remember the details about it, but yeah, I think we oversimplify it by saying it's just olfactory.
Oh, yeah, no, I mean, touch is very important. We show huge effects in humans. Oxytocin facilitating, responses to C fibers and so forth. I have one more question since I've got you. I'm also very interested in the mechanism whereby oxytocin may be influencing the brain by the vagus. And I wonder, because you've got such a fantastic model, have you ever kind of looked at the possible role of vagus stimulation?
No, we have not, but I think that's an excellent idea. Particularly because with intranasal oxytocin, you're getting some in the periphery, and there could be vertical signaling, through the vagus and doing all kinds of things that sort of maybe a different mechanism that you would expect that if it was just releasing in the brain, the hearing receptors in the brain. But yeah, I think that is absolutely an area that we or somebody should begin to look at. Because
I'll mention it in my talk because we're using, transcutaneous vagus stimulation, showing it can release oxytocin. It's also used for the treatment of depression and a number of other disorders now. So it's coming. Now you don't have to actually directly invasively stimulate the vagus. You can stimulate it via the ear. It's opened up in humans, but we can't do the kind of lesion studies, nerve central and so forth.
Yeah. Now, there's some nice studies in rats. I think rats or mice that from Valerie Vinovich and others groups showing that social touch, stimulates these oxytocin neurons to fire. So now we can actually see the neurons lighting up and firing whenever the animals are touching each other. So yeah, pretty cool. All right, thank you.
Lali, just one question from our audience. Will the precision mechanism be applied to the human being tomorrow?
Tomorrow, not tomorrow, but in the future. Yes, I think that definitely it can because, for example, combined behavioral therapy. So, if we can figure out what kind of behavioral therapies are effective, and then if increasing salience of social stimuli would help those be more efficient, then by giving oxytocin or somehow stimulating the oxytocin system, you can make those behavioral therapies more salient. And maybe you can also genotype people to find which individuals have a certain oxytocin receptor genotype that would make them more likely to respond. So, although not really tomorrow, but in the future, I really do think that we learn it's not just a drug. You don't take a pill in the morning. That's a bad approach that psychiatrists take, and just take a pill once or twice a day. You need to pair it with the right context, and that's what I mean by precision. Just pairing the drug with the right context.
Okay, thank you very much. Okay, so let's go to the next talk, which is by Ji Zhang. from University of Tsukuba and oxytocin receptor and diversity in social behaviors. Okay.
Can you see my screen now?
Sure. I have to put in a slide show mode.
Okay.
Okay, good.
Okay. So, hello, this is Jean. Thank you to thank Larry and Singapore give me this precious opportunity to present working ongoing project in Ireland. And the title of my talk is Oxytocin Receptor and the Diversity of Social Behaviors. Since the conference targets public, so I will make my talk as easy as possible. You can feel free to stop me anytime if you have questions. So we know that the pandemic produced by the COVID-19 continues to dramatically change our social lives, including especially also our family life. Okay, so it's crucial to understand the neural mechanism underlying social behaviors in families, including the parent family and maternal behavior, and so that it can help us establishing the well-being of adolescents and children in family in crisis situation. So since and also Higyaki and people they already give an introduction on oxytocin, or so I don't have to tell you what is oxytocin. And in our lab, we are especially interested in the neural mechanism underlying pair bonding behaviors. So everyone knows that in the animal kingdom, some animals are promiscuous. For example, the tigers and camelids. But some animals, they are monogamous. For example, the goats, and also the primary wolf, which Larry just showed us. And so oxytocin receptors have been shown to moderate pair bonding and parental behaviors. It's very interesting and also striking that oxytocin receptor shows extremely diverse expression pattern in different species. For example, here you can see that in primary wolf, which Larry just showed us. So here we can argue emphasize that in primary wolf, it's like the expression of oxytocin receptor is extremely high in the clear patterns and also in the bilateral amygdala. But in monkeys, we can say that it's very high in the lateral septum, and also, for example, the DT and the stage 3 campus, and also the different part in the basolateral, in different parts of the amygdala. So we think that not only across species, even within one species, for example, within primary wolf, there is also a big difference across different individuals. Because in here we show the two individual particles, and in the individual one, we can see that also the amygdala expression of OXDR is similar to the individual two, but in the nuclear problems, we can see that one individual shows very strong expression, but another one actually doesn't. And these two individuals actually also show the different behavior. So the individual with strong expression in their confidence, they can form their bonds much faster than the individual two. And statistical analysis showed that in nuclear carbons and coded treatment, we can see that there is much more variability in the expression density of oxytocin receptors. So our question is one is oxytocin receptor gene is so evolutionarily plastic, and so based on this question, we have two hypotheses. The diversity in the oxytocin OXDR regulatory sequence determines the species diversity of the OXDR expression pattern is our first hypothesis. And the second hypothesis is the species difference in the expression pattern of OXDR determines the diversity of social behaviors. Then, how can we prove if our hypothesis is proved or not? As Larry showed us, and in the whole, they are highly social animals, and the primary they are highly social animals, and they form pair bonding, and also they are by talented nurturing pair cups, and also shown that the oxytocin receptor has a strong spread in nuclear carbon and the basolateral major primary form. And on top of this side, the mouse usually they are polymers, and also the mouse usually they all the female mouse that take care of babies, and also often mouse sometimes the mouse infanticide, that means they kill their babies, and they are shown that in mouse the YTR expression pattern is quite different from both. Probably can say that here in the ECC and also in their carbon and also between the isolated neutral in mouse there's much weaker signal and so what will happen if we put the bones of oxytocin receptor gene component to the mouse and try to make a mouse which has we expect if this can realize they go that the mouse can replicate the expression pattern of the bone, and we will also say that the second process is the correct or not. If the mouse can become, for example, more air bonding, and also they become high power nurturing. So with the conventional transparent technique and put the local XTR3 with actually back long and then modified it with the coaching and in the spectrum and then put it in the fertilized eggs and then inject to the pseudo mother and then they got the transaction not happened. We can say that there's I totally without 10 models. Here I show for the representation models. We can say that there's it's really a surprise. In all those 10 models, none of them actually replicate the expression pattern which more on most of the receptors. Instead, each genre has a very unique split as the expression pattern of here is not with and simply determined by the sequence as an infant sequence, as a regulatory sequence of movement here cycle. Instead, the expression of here in the brain is very sensitive to the chromatin environment at the integration site. And another interesting thing is that also in the brain we got to work diverse expression I think works but in the memory we can say that the expression of the here is quite similar. So this means that it's in brain and memory domains actually oxytocin receptor genes they have a different mechanism regulating their expression. So this is actually very interesting because we know that oxytocin is actually the regulatory oxytocin expression is quite conserved. There's in 2003 actually what they make the transgenic mouse with the sequence from Tsukuba and actually they found that oxytocin, which is a homologous of oxytocin, they express exactly the same population of cells. So that means that oxytocin is high, the regulatory system of oxytocin expression is highly conserved. But for oxytocin receptor, it's proven by the experiment that it's actually still quite backwards. So especially interested in this two based because there's present almost complementary. So first, we did the the focal mouse with like particle structure. And it shows the results which we come from taking. And yeah, by this kind of truth tracking, we can say that with the which mouse, the focal mouse is better. And so here we can see that comparing with the wild-type animal mouse, the large history mouse, they actually showed a very distinct behavior in the first 10 minutes and the second 10, in the last 20 minutes. In the first 10 minutes, they spend significantly longer time with stranger, but then after that, they spend significantly longer time with their partner. This is very different from wild female mouse. And in wild female mouse, in the second, in the last 20 minutes, there's a tendency that they spend longer time with stranger than their partner. And we next also did the capsule retrieval test. This test is a paradigm testing the maternal behavior, and usually this is we put the three pups into the cage of a single house virgin female mouse, and then this virgin female mouse they will collect the pups together to their nest. Okay, so here I will show a one mouse from A3 line, and this video is 10 times speed. You can see that the mouse from A3 line, they very quickly to pick up the pups to their nest, and then start they start bothering them. And and then this video will show that another mouse from A4 line. You can see that this is also 10 times video. To make it faster. So we can see that this mouse it explores, but it never reaches the past. So this is already 10 minutes, 20 minutes. So it can.
The hormones, which are most importantly oxytocin in social behavior. But my talk is about this steroid hormone. For some reason, start doing the weird. Okay, so these gonadotropin hormone are secreted from either testes or ovaries, but these hormones is transported to the brain to act on the various brain area which is involved in social behavior neural network. Just briefly, what's the male-female difference to regulate this behavior? So, in the neonatal period, that's including prenatal and postnatal, early postnatal period, having a testosterone develop male types brain. On the other hand, during this period, in females, there is no testosterone secretion from testis or even nothing, even estradiol from ovary, nothing happens, and female brain is developed. But in the pubertal period, both testosterone and estradiol increase, and this also, to some extent, help the female brain become more female type and male brain more male type. So this hormone action is called organizational action, which is built neuronal network of social behavior. Once they reach, both male and female reach to the sexual maturity, estradiol from ovary and testosterone from testis will act on this specific brain side of social behavior network that cause a female type or male type social behavior. Of course, in females, this estradiol is secreted in the secret. Okay, so this steroid hormone action during the adulthood called activation action, which modulate neuronal structure of social behavior. And once this estradiol and testosterone enters the brain, testosterone can be also converted to estradiol by enzyme called aromatase. Then both in male and female, estrogen receptor is very important to regulate this social behavior network. Just briefly, in females, they show different kind of social behavior depending on their reproductive cycle. But I don't have time to talk about this today. I rather want to concentrate on male social behavior in my talk today. So male mice do not show any interesting behavior towards non-receptive female. But once they find a receptive female, they of course the male show male type sexual behavior, which is like this one. This is male. And also, if the male find another male mice, especially included to their territory, they will show male type aggressive behavior. So how this specific behavior regulated by steroid hormones. So this is kind of very rough sketch of the social behavior network in mice. And also I showed here two types of estrogen receptor, which is very important for both male and female social behavior regulation. And red is ER alpha and blue is ER beta. So as you can see, some area only has ER alpha, some area has both ER alpha and beta, and some area has only mainly beta. So first, to look at the effect, the role of ER alpha in these three areas, which has both, which express ER alpha. What we did was using RNA interference method with the use of adeno-associated virus, ALV, we knock down these ERR site specifically, either medial optic area, centromedial nucleus, or medial amygdala. And look at the male type social behavior, which I just showed you, male sexual and aggressive behavior. So, as you can see, this behavior was all disrupted by the knockdown of the estrogen receptor alpha in brain. However, some of the behaviors here were intact. So that means ventromedial nucleus hypothalamus is very important for the effect of estrogen alpha in the ventromedial nucleus is very important for even male sexual and aggressive behavior. But very interestingly, medial amygdala is kind of important part of the brain. Estrogen receptor alpha disruption did not do anything. Okay. However, in this brain area, if we knock down estrogen receptor alpha pre-puberty, so that means there's no estrogen receptor alpha in this brain area during pubertal period. Then both sexual and aggressive behavior in adulthood were greatly disrupted. So that's one thing that steroid hormone during lifetime, throughout the lifetime is very important. On the other hand, estrogen receptor beta disruption did not affect so much any behavior in any brain area. As I just showed here, and then even medial amygdala, we disrupt the estrogen receptor beta, nothing happened. So nothing happened for the male sex type, sexual and aggressive behavior. However, one more thing we looked at is when male confront both non-receptive and the receptive female, they usually prefer or investigate more receptive female before they actually show the sexual behavior. The male are facing both receptive female and intruder male. Again, they show if they have to compare these two animals, they usually show more investigation to receptive female. However, if we knock down estrogen receptor beta in the medial amygdala, what we found was these males no longer or completely and investigate more receptive female. So, thank you.
There's also a comment in the chat that